Welcome back for another private tour at the Western Museum of Flight. I'm Cindy Maka, the director. Prominent aerospace technical authority Ron Gibb will tell us about the history, performance, and technical specifications of one of America's greatest launch vehicle achievements, the Atlas rocket.
Hi, I'm Ron Gibb, and welcome to the Western Museum of Flight. What I'm going to talk about today is the space program display that we have here at the museum. And this was made possible because the aerospace industry in Southern California were major contributors to the whole space program from the start in the 60s with the launch of the first astronaut, the Apollo program, the space shuttle, and even yesterday's launch of the satellite to Mars. I have been involved in some of this in the 60s, and I'm just going to talk about a few things and share my experiences with you. Initially in early 60s, I worked for General Dynamics Astronautics on the Atlas program and worked on the launch of John Glenn, the first man in orbit for the U.S. Next, I worked to create a solution to a problem that had with Scott Carpenter and his flight. And then I worked on the first space vehicle that had liquid hydrogen, which was required to go to the moon. And then when the Apollo program started, I moved to LA and worked at Parker Aircraft on the Apollo LEM vehicle and also the S-2 space vehicles. Now I'd like to talk a little about the Atlas missile. It was a very unique design. It has three unique characteristics. One, it's not a single stage or a two-stage missile. It's a 1.5 stage. And the reason for that is the designers that created this were concerned that they would not be able to start an engine on the second stage consistently in space. And so what they did was they put a booster section on the bottom with two engines, and those engines have 170,000 pounds of thrust each. They have a third engine in the center, which is attached to the sustainer, and it has 80,000 pounds. And so all three engines start at liftoff, and when the booster section drops off, the sustainer engine continues to fire to be assured that they would have the thrust needed to get to the end of the flight. Now the second thing is, this missile was a stainless steel balloon. The wall thickness was 20 thousandths, which is a little thicker than an aluminum soda can or beer can. And this had no internal structure, and it could not support itself, its own weight sitting on the ground. It had to be pressurized all the time. But it did make an extremely lightweight vehicle. In fact, the whole booster, which is 65 feet long, the whole sustainer, which is 65 feet long and 10 feet in diameter, it weighs 5,000 pounds. When you fill it full of fuel, you put 240,000 pounds in it. And so the fuel to weight ratio is 46:1. The booster section with the two engines weighs 6,000 pounds. So the total missile is 12,000 pounds, 11,000 pounds. The Mercury capsule is 3,000 pounds. And so the launch weight of the Mercury Atlas system was 255,000 pounds. It had three engines, and that provided a thrust-to-weight ratio of 1.65. Ironically, the maximum G's occurred at the end of the flight when the tanks were getting close to empty, because you only had 5,000 pounds for the sustainer and 3,000 pounds for the Mercury, and you had an 80,000 pound engine driving that to a very high G level. Now, John Glenn was launched into orbit on February 20th, 1962. And that was 59 years ago. And on that flight, I was responsible for monitoring the pressures on the Atlas missile, and we had duplicate data in San Diego that was displayed at the launch platform control panel in Cape Canaveral. And so I was monitoring the initial pressure during the fill of the liquid oxygen, and then the pressures in the two tanks, the LOX tank and the RP1 tank, and to ensure that they were conforming to what was predicted, and then also monitoring the amount of helium that was used to fill the tanks when the propellants were expended. And there were three critical phases of the Atlas missile. The first one is at launch. You have a thin membrane between the RP-1 kerosene tank at the bottom and the LOX tank on the top. The LOX tank had 160,000 pounds of liquid oxygen, and on top of that you had a 3,000-pound mercury capsule. And when you started the engines, there was a sudden drop in the fuel level because of the initial surge of the engines. And there was only 25 cubic feet of ullage or vapor in the top of the tank. And the other thing is the inertia of starting the vehicle, the G-loads on the LOX and the capsule wanted to push the weight down and into the fuel tank. And so there was a very high performance helium regulator that provided pressure very quickly to maintain that pressure. If it didn't maintain the pressure, the bulkhead collapsed and the missile would explode. The second critical stage was going through maximum dynamic pressure, which occurred at 30 seconds into flight, and it reached a dynamic pressure of 1,000 pounds per square foot, and this occurred at Mach 6. And at this point there was a lot of buffeting and because of the flow and the loads. The third critical stage was when the booster separated from the sustainer, and the sustainer engine was still burning, and so when that released, there was a concern about any impact of the two separation. So those three things went smoothly. Toward the end of the flight on Don Glenn's mission, he ran out of liquid oxygen right at the end. And ironically, the planned velocity to escape into orbit was 25,700 feet per second. And he was within 7 feet per second of that planned estimate. So he was right on the plan. The problem is that he had a very high orbit, which was very favorable, and he didn't have much atmosphere to go through. And so when NASA analyzed that, they came up with the idea that if he had had a low trajectory orbit where he went through a lot more atmosphere, he would not have been able to get into orbit. And so they basically put a hold on the next flight of Scott Carpenter until they decided what they could do. It took 6 weeks to get this done, and Astronautics had provided analysis that said, well, we normally fill the LOX tank at 6 psi. You had to have at least 2 psi to support the mercury capsule, the 3,000-pound capsule. And if we moved down into that safety margin and reduced the pressure to 2.5 psi, that lower pressure would lower the temperature of the liquid oxygen and would provide more mass. So it turned out that if you did that, you could meet the low envelope margin and you could safely go into orbit. So NASA gave Astronautics an emergency directive and says, go do it. You have 6 weeks to do it before Carpenter's flight. And I was given the job to do that. And my boss said as I left to get this done, he said, well, please don't let me the guy that has to call NASA and tell them to scrub the mission. So I had 2 valves shipped from Cape Canaveral, put them in my car, drove to Norwalk. The company that had designed and built the valve was Peacock Engineering. And when I got there, it turned out there was nobody there that knew anything about the missile valve. Typical in the aerospace industry, the minute the contract ended, they laid people off, and the people had been laid off. So there was a challenge to understand what was happening on the valve. We then had to come up with a redesign. We had to have the parts made, and we had to install it, and we had to test it to make sure we did not go below the minimum 2.5 psi. Now, while we were doing that, NASA said, oh, we want you to do a full flight worthiness test, and that includes random vibration, and it means a maximum flow rate, and you have to do that and maintain LOX cleanliness, so when you get through with the testing, we can put it in the valve, we can put the valve in the missile and not have any problems or risk due to contamination. So we got all that done. It turned out that in order to do the flow test, there was only one facility west of Mississippi that could do that, and that was Wiley Labs out near Corona in Norco. They had a heat exchanger that would comply with the high flow rate. When the liquid oxygen was full in the tank and it was boiling off because of the thin wall, the flow rate out of that valve was 15 pounds per second. But when you first started to put liquid oxygen in, and you had a warm missile and minus 297 degree oxygen, the flow rate exceedingly increased to the point of 50 pounds per second, which was like the T-38 jet engine and afterburner. And so there was a lot of buffeting and problems with that, so we had to do that test. We finished all the testing on Saturday, the 19th of May, shipped the two valves to Cape Canaveral. They installed one on the missile for Carpenter, did a checkout, and everything worked fine, and he was launched on the 24th of May. And everything went fine and it worked great. Everyone was happy. Ironically, a few months later, two things happened. One, we received a big wooden crate from the embassy in Washington from South Africa. And we opened up the crate, and here are a whole bunch of Atlas parts, and there were two helium bottles, 24-inch diameter bottles. And these bottles did not have any burn marks on them. We checked the serial numbers, and they were from John Glenn's flight. Now, these were supposed to burn up over the Atlantic. His trajectory was way north of South Africa. And so the only thing they could come up with was that it skipped through the atmosphere. A farmer thought it was hailing out, went outside and saw these metal pieces in his farmyard, and it said General Dynamics Astronautics San Diego on it, and so they shipped them to us. This raised a lot of eyebrows because this stuff was all supposed to burn up. Nothing was supposed to come back. There was not supposed to be any hazard to people. And so they started thinking, well, maybe they need to do something different. The second thing that happened is I was informed I was under investigation for improper confiscation of government property. And in simple words, it was telling me I was a thief. And I was put under suspension, and because I had taken these two valves and hadn't returned them. Following the 3-week investigation, it turns out that I had done everything properly. I had the right paper trail. When we reworked those two valves to the new configuration, you change the dash number and you put a new nameplate on it. But both of those valves were been launched and had burned up in the atmosphere. And the investigators came to the conclusion that if the government had just made a simple phone call to me, I could have explained the whole thing and I could provide all the paperwork, and there were no problems. While I was doing this, I was taking classes at UCLA on rocket design. There were graduate classes that UCLA was providing to support the space program. And one of these classes talk about the trade-offs of going to the moon. And do you go directly to the moon from the Earth and then come directly back? Or do you go into a parking orbit around the Earth and then go to the moon? Or do you then add a second parking lot or parking orbit around the moon? And when Wernher von Braun selected the Saturn V configuration for the Apollo, he elected to do 2 orbits because that was actually the lowest cost solution. The fuel that the Atlas used was liquid oxygen and kerosene. Now, this was the best propellant in the atmosphere, but when you get out of the atmosphere, the best propellant is liquid hydrogen. Kerosene has 4 times the energy of liquid hydrogen, but liquid hydrogen is 1/12 the weight of kerosene. So when you get out into orbit, then the liquid hydrogen, being a lot lower weight, was much more efficient. And so the initial plan was it was going to take 1,000 pounds of fuel and missile to go to the moon, for 1 pound to land on the moon. And based on the Apollo 5, the Saturn V and the Apollo configuration, a 6 million pound rocket landed a 15,000 pound space vehicle on the moon, and the ratio was 400 to 1. Now, in order to go into the parking orbit with liquid hydrogen, which is at minus 423 degrees compared to minus 297 with liquid oxygen, you're in a zero-G condition. And so NASA had given astronautics a contract for the Centaur, which was to develop the technology for a liquid hydrogen system. That was the first system in space. And there were two things that had to be done. One, none of the seals worked that you had with liquid oxygen worked at minus 423 degrees. So I was involved in 6 months of developing seals, both static and dynamic. And ironically, one of the best materials was gold-plated hollow steel O-rings that could be collapsed and provide a seal. The second thing was going into a parking orbit, you have a zero-G condition. And liquid hydrogen boils off very quickly and the pressure builds up very rapidly. And so you had to vent that pressure. Well, in zero-G, you don't know where the bubble is, you don't know where the gas is, whether it's one big bubble or 10 bubbles or 1,000 bubbles. And so the challenge was, how do we do that? Well, the manager I worked for was raised on a dairy farm in Wisconsin, and he said, well, maybe we can use a cream separator concept. We'll make a disc that rotates so that the fluid flows off the disc, and we'll put the vent holes at the end of the disc at the tip so that the gas can escape back into the disc and be dumped overboard. And so we designed a zero-G vent valve, and because of the gyro effect from a rotating vehicle, we had two discs, one rotating the opposite of the others. And this was tested, but there was no way to test it in zero-G, and we never knew whether it was going to work until it got into orbit. It did work, and the Centaur program was used to launch the Surveyor to the moon before the Apollo program landed there. At the end of the Centaur activity that I was involved in, astronautics lost the competition for all three launch vehicles for the Apollo program on the Saturn V. And because of my experience in liquid hydrogen and liquid oxygen, I decided to take a job with Parker Aircraft, who was located at the entrance of LAX. They had a 10-acre facility on Century Boulevard, and they had quite a few contracts for the Apollo missile with liquid hydrogen and liquid oxygen. And I worked on 4 or 5 different valves there. The last thing I worked on was the oxygen regulator for the LEM vehicle, which was being built by Grumman. And typical regulators require a pressure band. Because they use a coil spring, when the valve opens up, in order to increase the flow and increase the throat diameter, you have to increase the pressure. And so you have a pressure range that can be fairly wide from the starting point to the max flow point. The designer that created the design for Parker Aircraft came up with not using a coil spring, but using Belleville washers, which had a spring load. And he was able to come up with a negative spring rate so that as the valve increased in flow rate, the pressure did not change. And so the minimum pressure of opening versus the max flow pressure on the oxygen regulator for the LEM vehicle was 4.8 psi. And because of the Belleville spring, it was very compact and very small, and the total valve weighed 1 pound. Now, when you look at what happened on Apollo 13, and they made a movie about it, when the oxygen tank blew up on the service module, all 3 astronauts had to go into the LEM vehicle. And the LEM vehicle was designed for 45 hours for 2 people. It was going to take 90 hours to get back home, and there were 3 people in there. But because the regulator could be reduced in pressure and because it had a very efficient operation, they were able to calculate that they could get the 3 astronauts home and have enough oxygen. The only big problem they had was they had to figure out how to get rid of the carbon dioxide, and that is graphically demonstrated how they band-aided that and got that done in the movie. But anyway, these are some of the experiences I've had. I'm very grateful to be able to work on the program, and it's ironic, I didn't even know about the oxygen regulator on the LEM vehicle until after Apollo 13, which was years after I left Parker Aircraft. Anyway, I hope we can see you here at the museum and see some of our displays. So.